Welcome to Liquids and Solids. Now, water, very unusual substance that I've emphasized from the beginning of this course. We'll start out with its characteristics. Water changing from solid to a liquid requires 6.02 kilojoules per mole, but changing from a liquid to a gas, it takes 40.7 kilojoules per mole. Has a strong dipole moment, which we talked about. Its attractiveness between the molecules is less the further away from each other they are. And some of the characteristics of water that are really, really interesting is that vapor pressure, which I'll mention again later on, is heat of vaporization is so high that when the sun shines on the planet, that the absorption of that heat from Sol, that's the name of the actual star, it's not the sun, its actual name is SOL, Sol. That much energy is absorbed by water as it vaporizes. It keeps the planet from getting too warm. Same kind of thing happens when you get out, you perspire and there's a breeze blowing and you cool off. The absorption of the heat from your body as the water vaporizes allows the cooling of your body. That's really high. Also, think about capillarity. That evaporation of the water from the top leaf of that giant redwood was, 40.7 kilojoules per mole. Huge amount of energy, which again accounts for that fabulous capillarity, which brings up another molecule. All right, back to dipole moment. This is an attractiveness of molecules with distance. It's not real strong with the polar because the distance makes a lot of difference. With covalent and ionic compounds or solids, it's quite a bit greater. Exceptions to this, like there are exception to most chemical rules, and that's hydrogen with oxygen, fluorine, and all the others in that column with fluorine. This is called hydrogen bonding. You'll hear lots and lots of hydrogen bonding for the rest of this course. It has a lot of unusual side effects, but one that's most important is high boiling point. Water, hydrogen fluoride, and all those kinds of things shouldn't have a boiling point as high as they do. We're real glad because that is another thing that helps baffling the energy of Sol. Okay, next is London dispersion forces. Noble gases and nonpolar molecules have these. There is sporadic attraction, usually indicated by low freezing points, much lower than you would think. Temporary dipole moments, this is caused by your electron cloud, is pretty large. And by law of probability, with things moving so quickly in a confined area, you're going to have a one-sided cloud periodically creating a charge on one side. It's called a dipole moment. And again, multiplicity of high-speed interactions. Now, one of the things that's interesting about the polarity of these substances is, I mentioned the meniscus. When you put water in a tube that's inch across or so, it dips. It has a little dip called the meniscus. Well, you put the same amount of mercury in such a tube, it dips up. And that's because of the attractiveness of the mercury molecules for each other. Higher density, much higher density. 13.6, I think it is, compared to water with one. Okay, another one here. Let's see, what else can I That's about it. Next, we go to structural. Um, Solids are comprised of amorphous and crystalline. They're multi parts, but the main ones are cube, body centered, and face centered. Notice my fantastic artwork. Please do not make disparaging remarks under your breath, even though they're definitely earned. Now, the way you measure this, I had a professor back in the 60s by the name of Erwin Selleck. He got his PhD in X-ray diffraction analysis. So he was really into crystals. X-ray diffraction grating measures the distance between the layers of the crystal differences, if you wish. And I have an example, aluminum crystal. I bet you didn't know that aluminum actually forms crystals in certain characteristics. The wavelength is equal to 1.54 angstroms. A with a little circle above it, it's called an angstrom. Theta, which is the angle, is 19.3 degrees. And N, which is a number of molecules, a number of moles, we'll say is 1. The question is, calculate the distance between the crystal planes. Now, the diffraction grating formula is xy plus yz equals 2d sine theta. Or if you group it all together, it's n number of moles times the wavelength is equal to d sine theta. Now, d is equal to, if you solve it for d, because that's what we're after, is the distance between them. Incidentally, that formula is called the Bragg equation. Everything has a name because it was derived by somebody. So, and if you reevaluate it and solve for d, you get d equals n lambda, which is what the wavelength sign is, times 2 times the sine of theta. And you multiply that out by simple multiplication, you come out with 2.33 angstroms, or 233 picometers between the faces of the aluminum crystal. So all this stuff can be calculated, it just takes time. Ionic solids work well with polar solvents. Ionic solvents, solutes or solids, obviously salt dissolve in water readily, salt being an ionic solid, water being a polar molecule. This also works as far as conductivity also. Molecular solids, not so much. Their lattice points contain molecules on the corners. Now, a crystal of an ionic solid has an ion at each one of the corners of the crystal, thus making it, more plausible for dissolvability in a polar molecule. But the molecular solids don't. And believe it or not, ice is an example of a molecular solid because it has water at its crystal points, its lattice points. And so is sugar. Okay, let's get some rules because we always have to have rules for everything. Atomic solids have atoms at the lattice tips, which I mentioned. Molecular has molecules at the tips. Ionics have ions at the tips. And there's a few others that are kind of interesting for study. Metallic, closely packed, and they have what's called a common electron effect because there's so many electrons in such a fixed area that it has an unusual effect called the common electron effect. Network solids are interwoven, large numbers of atoms interwoven in a fixed area, but not in a crystal organized way such as metals would have. And then column A, the elements. That's the noble gases. They have really low melting points, less than 200 below zero, uh, most of them. And they really shouldn't have, but because of their unusual, shall we say, attractiveness for each other, even though there isn't a great deal. Then one that I suggest you read up on, because it's kind of neat in this day and age, because since the time these laws were formulated, carbon and silicon network atomic solids give you all these fantastic carbon solids that are used in automobiles and pan cooking utensil solids, and the silicon solids are you're probably quite familiar with in reality, but all of this was theorized way back when. Okay, next we're talking about the vapor pressure of water being 40.7 kilojoules per mole. This allows life on the planet, as I mentioned, and the planet you live on is not Earth, it's Terra, Terra. Earth refers to solid soil. So you live on planet Terra, allows you to sweat and release heat with the evaporation of the perspiration. Generally, larger molecules have a lower vapor pressure. As temperature increases, the formula for it is the natural log of the pressure of that vapor is equal to minus the change. Delta always means change or heat, the little triangle of the vapor divided by the universal gas constant for this, which is 8.3145 joules per Kelvin times moles, which we'll talk about in a minute, times 1 over the temperature, which in this case is Kelvin, plus C, which is a constant of a given liquid. Each liquid will have its own constant. So if the heat of vapor for water is 43.9 kilojoules per mole, what is the vapor pressure at 50 degrees centigrade if you got water at 25 degrees centigrade and its vapor pressure is 23.8 torr? Well, the formula is natural log of the partial pressure, or the vapor pressure of at temperature 1 over the vapor pressure at temperature 2 is equal to the change of vapor energy divided by R. And again, it's times 1 over T2 minus 1 over T1. Now, you see these in centigrade, you know immediately you're going to have change in the Kelvin. And you just add 273 to the centigrade temperature. Thus, the natural log of 23.8 torr divided by the pressure of the second temperature is equal to 43,900 joules, because remember, that's kilojoules, divided by R, which is 8.3145 joules per Kelvin mole, times 1 over the two temperatures subtracted. First one's 32.3, and 25 degrees is 298. So you subtract those two, and fill in and grind, as I've constantly referred to it. Later on when we do problems, I'll say fill in and grind. It gives you 1.37, and the way you find that is you look up the anti-log of 23.8, or anti-log of 1.37. All right, so it's 23.8 over pressure, vapor pressure of the second temperature, and that'll equal to 0.245, or again, when you reverse that, you come out with 93.7 torr. In other words, you divide 23.8 by 0.245, it comes out to be 93.7, and your pressure is in torr. That's how you work one of those problems. Looks sort of complicated, sounds sort of complicated, but again, you can blow these screens up full screen, and if you sit there and look through it, it's actually pretty logical and pretty straightforward, pretty easy. Now, it's a minimal covering for solids and liquids. You can bog down in the weeds and spend probably days on this. But for a general course, I feel this is an adequate introduction, which again is my purpose here. From now on, we're going to delve into things more easily understood, I think. So